A particular case is this periodic disturbance. And we said if the disturbance has this periodic structure, then what this feedback controller has to do is to include, if I write C as BC, AC, and this is a periodic, then a condition for this output, let me use continuous time, discrete time case. The condition for the output to asymptotically go to 0 is that you have to include a model of the disturbance inside your controller. And I call this model AD. For repetitive control, AD equals 1 minus C negative n. This is for repetitive control. Okay, that's the simple idea, internal model principle. Then we discussed the particular cases. So we arrived at this conclusion that I have to include AD. But what about designing BC and AC prime? We talked about two approaches to design AC prime and BC. First one is pole placement. Okay, we discussed conditions for this pole placement to hold, to have a unique solution for the BC and AC prime. We discussed that. And then we discussed what we call prototype repetitive control, RC. The idea is pretty simple. Is if my plant is called BP divided by AP, then one simple approach to design this controller is I do cancellations. We discussed feed-forward approaches where we used heavily the concept of model inverse. So this, I include the inverse model of the plant over here. And then additionally, I will include the internal model of the disturbance. And then I include the KRC negative N plus D. Okay. So 0, 2, such that the closed loop will be stable. That's one way to do. Then we discuss this. Now, things works perfectly fine if I have perfect model, if I don't have this uncertainty term. Things works perfectly well. Now, if I have some slightly different model, different plant, I have this uncertainty inside. I did the example last time. And then we showed no matter how we design KR, as long as KR is larger than 0, then the closed loop system is not stable. So that means this design by this structure itself is not robust to plant uncertainties. So at the end of last lecture, we came up with this conclusion last time. So to make the controller robust to plant uncertainties, do instead, here, instead of using a perfect internal model, do some modifications over here. Add a Q here. Q is a low-pass filter. Add a Q here, both in the numerator and in the denominator. Then the conclusion is that this will make the system have robust stability. Okay? So now, look at this structure and have some intuitions here. I said Q is a low-pass filter. So that means at low frequency, Q is approximately 1. So that means we have approximately this internal model valid at low frequency. What will happen if at high frequency? A low-pass filter will be approximately very small. So let's say it's if Q is 0. Unable to reject the disturbance, is that what you said? Just take a look at a little more. If Q is approximate, let's say it's 0, what will happen? CZ is what? 0. So that means we are not doing control at all. In that case, although we don't have the disturbance rejection, but at least we that's like compromising between good disturbance rejection performance and stability. That's the intuition for why this structure is robust in this sense. Okay, so some more details. Low-pass filter. There are a lot of low-pass filter designs. One particular case is use this structure, zero-phase low-pass filter. It's zero-phase because of what we learned last time. If you look at this Z and Z inverse, they are complex conjugate of each other. So when these two terms add up together, their phase cancels, and all these other terms are real, so they have zero phase. Okay. Some more. Yes. Not in this case. So when we say stable system, we mean the plant itself is stable. So if something is stable, you add disturbance to it, you won't destabilize the system. The output might look still not very good, but the system itself is stable. Mm. So you mean in this kind of structure, in a feedback structure? Mm-hmm. However, what you said is partially is correct in the sense if I have a closed loop system, then the input can destabilize the system, right? If I have a closed loop system. But what I said is if C is 0, in that sense, this is 0. So this is an open loop system, right? Open loop system, if it's stable, it's stable. Mm. Yeah, so when we talk about, for example, just consider a transfer function, for example. Let's say if my transfer function of the plant is simple example, 1 minus 0.8, z negative 1, 1. Let's say this is my system. This is the plant. And no matter how you inject disturbance in the system, or even in the case you have an open loop control. So open loop control, if you have general UK. Just to consider this system itself, is it stable or unstable? Stable, right? So that's what I meant. Yeah. If the plant is stable, then regardless of your disturbance, it's stable. All right. So last time I told you to, as an exercise, to prove that to prove essentially this case. So to prove that if I have perfect models, these poles, these closed loop poles, will be stable under this plant uncertainty here. Not under plant uncertainty here, under the condition. Let me write it for you. This is the question last time. Okay. Under this design, under design of 1, what are the closed loop poles? That's the question. Okay. When delta is 0. That's the exercise last time. I want you to understand I wanted you to prove last time that these poles are all inside the unit circle. That's the question last time. So take a moment to consider this problem while I look up for something from last time. Okay, anyone has any conclusions now? Where does the closed loop poles come from in this case? Say that again. A, B, C, B, C? Times the, do I have to put anything or just times it like this? And then? G minus D here. A, what is A here? So my notation is AP. BP. Yeah, that's the idea. So that's the something to start with. Then I actually want it more specific, but this is the correct way. You are on the right track. My C is KR Q Z inverse Z negative N plus D AP 1 minus Q Z negative 1 Z negative N. Let's do this exercise together to see how things go. So I'm going to have now I'm going to shift the denominator here to the left to get AP times this guy, which is going to give me AP BP minus AP BP Q Z minus N plus Z negative D BP, running out of space, BP AP KR Q Z negative N plus D. Let me see if there are any typos. I think this is correct. Yeah. So now I see, observe that I can factor out AP and BP. Inside, I'm going to have 1 minus, the first term is Q Z inverse Z negative N. And then here I'm going to have, if I factor out BP and AP, the remaining part is going to be K R Q Z Z inverse Z negative D times this guy. So it's Z negative N equal to 0. Okay? So now, inside, let me combine these two terms. I'm going to get 1. Let me see, I use plus or minus, I think. Let me try use minus first. 1 minus Q Z Z negative 1 Z negative N 1 minus KR. Okay. Let me see. All right. So remember, now the closed loop poles come from here. So you see, the closed loop poles first contain the roots of AP and BP equal to 0. Okay. So this is where the poles of the plant come from, and this is where the zeros of the plant, poles and zeros of the plant. So you see, we have to, what are the requirements for the plant in this case? The plant has to have stable poles and stable zeros. That's the assumption. So, and then the second term, we're going to have this. What are the roots for this guy, for this equation? Okay, so that requires a little bit algebra. I want you to have first a little bit intuition first. So we mentioned last time, if KR is in the range of 0 and 2, what will the magnitude of this guy be? The magnitude of this term. Less than 1, right? What about the magnitude of this guy? I said it's a low pass. So the magnitude of this guy is less than or equal to 1. Okay? Now, if these conditions hold, what will be, I was looking for this picture for you last time. So keep the structure of this equation in mind. And then I'm going to review something we obtained last time. So something we obtained last time is, let me turn off the, okay. So something we did last time is analyzing the roots of this guy. Okay, we did this. So what we concluded last time is, if this term has its magnitude less than 1, then these roots are expressed over here, are all inside the unit circle. Okay? So you see here, if you understand that, then things are exactly very similar here. Now it's just a matter of, I have another term ahead of this. But this term is, the magnitude is less than or equal to 1. So something less than or equal to 1 times something less than 1. Then these two terms combined together, magnitude less than 1. Right? So you can spend some time, write out the roots of this guy, but it's going to be stable inside the unit circle. That's the conclusion to make. Okay? So now you see, if we do that design, the message is the closed loop system is still stable. Now, another message coming out of this, which is slightly more important, is this concept. What are the open loop poles of this block diagram? What are the open transfer function from, let me just be more specific. What are the open loop poles of PC? Well, I meant open loop poles. If I meant what are the open loop poles in this case? So it's going to be the poles of the plant. Then the poles of the controller, right? So the poles of the plant are all stable, so we don't need to worry about that. The poles of the zeros, now something very interesting comes up. Remember, so the poles of the zeros will come out of here, okay? Now, last time, we analyzed for the version that's not robust, the poles of the open loop poles is going to contain the roots of these guys, right? Which are on the unit circle, you see? So now, if you do root locus analysis, if they are on the unit circle, then as long as you have a little bit of KR, the closed loop poles is going to be unstable. Now, things are different. If my poles are inside unit circle, let me say it's here, or I don't know, maybe here. Okay, if my open loop poles are inside the unit circle, you see, now I have some margins I can go before I reach instability. So if in this case, if the arrows are still going in this direction, I have this margin of this stability margin to go, right? This is exactly the intuition for this slide here. Okay? Now, look at this guy. The question, let me ask you the question. Maybe it's obvious to you now. What are the open loop zeros or poles? Always confuses me. Are the open loop poles inside the unit circle or not, if I do this design? You see? That's exactly what's happening here. So by making this part, this guy, I told you the magnitude is less than 1, right? So by making something low-pass design, I can shift these marginally stable open loop poles to be inside the unit circle. And by this design, I have gained the stability robustness. Okay, that's the central idea here. Yeah, so that's actually a very good point. It turns out, we explained several lectures ago, plant uncertainties are large at high frequencies, right? So that means at high frequencies, marginally stable poles are dangerous. So usually, this is the usual case, it's more important to shift these high frequency poles to be inside the unit circle. Low frequency poles are not that severe because, let me show, there are too many marks here. If you zoom into this picture, this is what you will see. I have a pole here, and I have another pole here. This is the marginally stable poles. The root locus actually goes like this, goes like in this way, and then out. So you see, even if it's marginally stable, but first it's going to go inside before it reaches instability. You see, when it's still here, it's stable. You mean this pole might be here? This. You mean this pole might move to 1.1? Not in this particular case. So when we talk about uncertainty, right? For example, I say P, the plant is P1 plus delta. This is the plant. Okay. What our assumptions are, this uncertainty term itself is stable. So that means the poles of this guy will be stable. It's not going to go outside the unit circle. Yeah, if this guy is unstable itself, it's going to be fundamentally much more challenging, the problem. Yeah. All right, so we have now finished discussing this stability robustness. I showed you some intuitions of this design. And then I mentioned one thing. Okay. I mentioned if you think about this closed loop poles, it's going to contain the zeros of the system has to be stable. That's one thing that we assume. In practice, what shall we do if the system has unstable zeros? That's exactly this slide, what this slide is talking about. So it's an extension to the discussions we have made. Suppose not all zeros of the plant are stable. So let me do this factorization, which you have seen previously in the zero-phase error tracking control design. So I factor out this to contain the stable zeros and unstable zeros. I think my notations are stable zeros is plus, unstable is minus. Okay. So BP minus is the uncancelable part in the zeros. Now, the design, the extension here goes as follows. Is this design. So take still the structure. In this case, I'm doing the idea internal model case. So I haven't included this guy yet, but we'll do that later. So the idea is still include the internal model over here, and then include this AP, which is going to cancel this AP here. But the different thing is you don't perfectly cancel this BP. Instead, you only cancel the cancelable parts, BP plus, the parts that are stable. Okay? But do this, and then do this extra step, a little bit extra step. Here, also here. Okay? Do these two terms. Okay? So my notation is still going to be BP inverse Z is going to be equal to BP Z inverse with every Z inverse replaced. Just a review. Replaced by Z. That's the notation we used from last time. Okay? And this B has this inequality here. Now, take a moment to look at this structure. Then I want you to be able to show that this system, this closed loop system, is stable. Okay? Actually, I want you to show two things. First thing is, if the system, if not all zeros are stable, so two questions, perhaps. Question one, if BP inverse is not cancelable, show this design, show C equal, the original design, essentially. BP KR AP Z negative N plus D. Show that this guy is not stabilizing the loop. Okay. Probably you already have some idea why this holds. Actually, this can be a tricky question. Not many people will be able to prove this part. So I want you to be very comfortable proving this part. Now, the second question is, if I use this new design, if I use equation 2, is stabilizing. By stabilizing, I mean the closed loop system is stable. So, two questions for you guys. Let's spend maybe 3 or 5 minutes to do this part. Okay? Okay. I'll be right back. All right. Anyone has any? Anyone has finished these two questions? Yeah. Second part is a little bit difficult. Yeah, I can understand. Second part is a little bit slightly more difficult. So let's do this now. Let's do this together. So you can see. So hopefully you already have some idea of how the structure goes. The first part is easy. Anyone wants me to go first part? The first part is essentially saying doing unstable pole zero cancellations is not good. Okay. So if you don't, if no one wants me to explain this part, I'll go to the second question now. So what is the characteristic polynomial you finally obtained? This part should be relatively easy. Characteristic equation. So which is coming out of the conventional way. 1 plus PC has to be equal to 0. And you do this factorization. What is the characteristic polynomial? Anyone? So it's going to be, let's see, let me do this. I haven't written it down myself. So if we're going to do this, it's going to be z negative d bp ap times kr z negative n plus mu ap bp inverse z negative mu, then 1 minus z negative n bp plus z negative d b equal to 0. Okay? So multiply AP and this term on both sides. We are going to get the result of, let me write a new page. It's going to be AP BP plus z negative d b 1 minus z negative n plus z negative d bp kr z. So mu and negative mu cancels. I'm going to get AP BP minus. Okay. So if I hadn't made any typos, it's going to be AP. No, I have to be careful now. AP, because BP is BP plus. So let me write it in the original structure. It's this guy. So I can factor out this BP plus term to get BP plus. I can actually also factor out the negative D term. So these are the common terms. Inside, I'm going to have B 1 minus Z negative N. What's this here? Plus, this guy is factored out. So I have 1 BP minus term remaining here. And then I have KR. I have Z negative N. I have AP is factored out. I have BP minus. Be careful. This BP minus is this guy. Yeah, that's my the full expression. So the poles, the roots of these guys are all stable, so don't need to worry. What's essential, what's different is this guy. So we got to be able to figure out that the poles of this, the roots of this polynomial are stable. So let's see let's see. I think we need to do a little bit factorization. So this is what I will try for the first round. So I'm going to divide by b, z negative 1, bp inverse z b. Then I have kr z negative n. Okay, so this equals 1. Let me use plus 1 plus b bp inverse z negative 1 bp inverse z kr minus 1 z negative n. Did I make any typos? I think result if I didn't make any typos. All right? Okay, so we got to be able to show that the roots, if I assign it at 0, the roots of this guy is going to be inside the unit circle. Okay? What is the let's see. What is the magnitude of this guy? The magnitude of this first term. Remember, the assumptions are, if you look at the assumptions here, B, this is the assumption of B. So I'm going to write it for you. The assumptions of B are B larger than maximum of omega, BP negative, EJ omega square. This is the assumption of B. If I have this assumption, what will be the magnitude of this term B? Less than 1, because J omega. Then you evaluate all these. Then the top part. So let's take a look at the more details here. So the frequency response is going to be BP inverse E negative J omega, BP inverse EJ omega, right? Divided by B, divided by B. If B is larger than the maximum of these guys, then you see the top part is nothing but BP minus EJ omega square. So you see, if this guy is larger than the maximum of this guy, then the magnitude is going to be less than 1. Okay? So now, if that happens, what will be the magnitude of this scalar ahead of it? The magnitude of this guy. So, yeah, it's going to be less than 1 in the end. Let's take a look at the details. I think the most convenient way probably to do is, so the assumptions are KR is in the range of 0 and 2. Okay? I think probably it's going to be very convenient to draw a picture maybe. Let's see. So this term is something minus 1, minus 1. So it's a vector that's going to be some number minus 1. And this number itself, what's the magnitude range of this number? It's going to be, if KR is between 0 and 2, and this is less than 1, then this whole thing is going to be between 0 and 2. So the range is going to be like this. So it's going to be in this range. I hope I have a red pen. Thank you. So the range is going to be like this. You see? It's the, if I write it as a vector, so it's going to be a vector that looks like this, okay? And you see, no matter how I change in this range between 0 and 2, the length of this vector is always less than 1. Okay? So you see now, this guy is always less than 1. Then coming back to the old topic of the distribution of the roots. Now, I think it's good time now to talk about the intuition of these roots. So I have 1 plus something, I don't care what is this number, but this number is magnitude less than 1. Magnitude less than 1. Then z negative n equal to 0. So the roots is going to be coming out of, if I multiply z to the power of n on both sides, I'm going to get z n equals negative of this thing. Okay? And this magnitude is less than 1. So you see, no matter how, I don't even need to compute the roots. I know the magnitude of the roots is going to be less than 1. Right? So that's the very quick observation to see that the root, again, magnitude is less than 1. This is important. Okay? If I'm going to have something, n roots, I have n roots, then the power of this roots to the power of n has magnitude less than 1. So if this is 1, then the distribution of the roots is going to actually look like this. I did a bad drawing. This is not a circle at all. It should be a circle. But the roots is going to be distributed on this circle. Okay? And the radius of the circle is less than 1. Okay, so as a summary, this is the key steps of this proof. So if we want to prove that the poles of this system are stable, then write out the characteristic equation. And then some of the key concepts you're going to need. First of all, is this guy has magnitude less than 1. Okay? Because of that, if we do this, the magnitude of this guy is less than 1. Then finally, you reach at this equation where this part, the magnitude is less than 1. Okay? That's the basic picture of this proof. So finally, it's pretty straightforward. I mentioned this is the case for ideal, perfect internal model. Now, you can imagine, if I have Planck uncertainties, then what we're going to do is just include, again, low-pass structure. Make it not perfect internal model, but we compromise that for robust stability. Okay, so let me see. The repetitive control part is almost finished. Finally, we can take an example together. If I have a disturbance, periodic, the period is n, and I want to design a controller. I think I'm designing the prototype repetitive controller here. Then if the plant is like this, so I think at this stage, probably it's a good idea to get used to this kind of notations where I use z negative 1 in the transfer function. So you can see here, get used to this and be able to develop this concept that quickly recognize the poles of this system is going to be 0.8 and 0.7. Okay? Very quickly get familiar with this notation here because we're going to use it very soon again. Then if I do, so you see here, the poles are all stable and the zeros are all stable. So I can directly use the, I don't need to do this extra step of extension that we have down here. I don't need to do this extra step because the system is already has stable poles and zeros. So I can then design this controller that cancels the plant by here, cancels the plant here, And then this is the modified internal model. Okay, the design is you see, once you figure out, once you have the design procedures, the design itself is very simple. The tough thing is showing that it's valid and works in many, showing the robust stability, the general stability. That's usually slightly more difficult. Okay, you can. That's relatively the end of this topic. So, as a quick review, we talked about internal model principle. Okay, we talked about the two theorems of internal model principle, and then this is a special case. Repetitive control is a special case of application of internal model principle. Well, you have this disturbance structure. Okay, so at the moment, take a moment. If you want to read more, take a look at the reader, the course reader. It contains several more extended topics. At the moment, don't take a look at these yet. Do not take a look at these yet. We will revisit these two references after we learn, probably in the next lecture. Okay. I have some time. I think I can start introducing a tool that is very useful and very intuitive to design as well. Okay, it's called Disturbance Observer. And the big picture, so this is a feedback design approach. First of all, this is a big picture. It's feedback design. Okay, so it's for disturbance rejection. Repetitive control is a type of disturbance rejection, and this is another type of disturbance rejection control technique. The basic idea, the big picture, is pretty straightforward. So you know, at this stage, you're very familiar with the concept of disturbance and uncertainties, particularly in mechanical systems. These are very common. So you also see that in all these learned techniques, for example, zero-phase error checking, even a very basic observer design, you need system models. You need the ABCD matrices. Okay? And this is inevitable to have uncertainties in actual mechanical system. You have seen that. System is subjected to disturbances. You have seen that. Okay? So to handle these very practical challenges in control design, there are relatively two related control techniques. First technique is robust control. The second technique is adaptive control. Robust control is saying you have some nominal information. You know how the nominal model of the plant looks like. Nominal model of the plant. You know this guy. However, the actual plant had some uncertainties and is different from this nominal design. How you can design your control scheme to make the design robust to these uncertainties. That's robust control. Adaptive control is a little bit in a different category. Adaptive control can handle several cases. For example, you have unknown plant. Your plant, you have no idea how the parameters of the plant looks like. Unknown plant. Then you identify these unknown parameters ahead of design controllers. Or adaptive control can also be used. You have unknown disturbance parameters. Disturbance parameters. Okay, we'll talk about this probably in a few more lectures. So you know the disturbance has a structure, but you don't know how the structure looks like. As a simple case, it might be possible, just an example. You know the disturbance, then you have to design your control. So one thing you can do is to identify this guy when you do your control design. So and let me show you why is a robust control example by this picture here. The basic picture looks like this. Okay, so inside we have one, two, three, basically three main components inside. The first component, G, U, V, my notation is going to be G sub U, V is the dynamics between U and V. Okay, so in more details, this is what I mean. The dynamics of the system is like Vs, the output, is GUVs times the input plus the disturbance. Okay, and when I use GUVN here, when I have a superscript n here, I mean it's a nominal model. It's a nominal model of GUV. Okay, and GUV is an actual. If this is the actual dynamics, then this is the nominal version. So disturbance observer, it's implementing its structures such that somehow this whole scheme is going to be robust. Okay, we'll talk about details, but this is the general intuition. If you look at the structure, it's actually not so difficult to understand the intuitions inside. So let's first take a look at, forget about all these mathematics. Let's just take a look at this block diagram here and see how things are going here. If I focus on how this signal U goes into the system, the signal U goes into two passes. The first pass is here. So it goes through identity line. And the second pass goes through here. It first goes through the plant. And then it goes through, pay attention, it's the inverse of the plant, of the nominal plant model. So if these two matches well, what will be this product? What will be GUV, GUVN inverse? It's going to be approximately 1. Okay? So you see, pay attention, this is plus and this is minus. So you see, if the system has good models, the information of U is going to get canceled in this summing junction. However, on the other hand, the disturbance information here, can I borrow your red pen again? The disturbance information, you see, look at the path. There's nothing that's going to cancel the disturbance on the left-hand side. The disturbance is not going to go here. So the disturbance path, it directly goes through this path and then here. Right? So if Q is 1, let's suppose this is an ideal case. If Q is 1 and these are good, then you're going to see this is going to cancel with its inverse model, and then this is 1. So you see D hat is approximately DS by this construction of block diagram. Right? And then look at this minus sign. Pay attention to this minus sign here. So I have some estimate of the disturbance, and I have minus sign here. This guy is going to cancel the actual disturbance through this construction of block diagram. Any questions? That's the intuition. Okay? Now, what will happen if the system has uncertainties and this nominal model is not characterizing the actual model? From here, you can do some analysis. You can write down the transfer functions between each signals here and then analyze the result. But the main message, one of the key messages is this. If QS is 1, then write down, let's do this together. Write down the actual control signal over here, US, out of this block diagram. Okay, so let's do this. Let me redraw the block diagram to make it more clean. Negative plus 1 divided by G U V N G U V. And then this psi is the measurement noise. Measurement noise, and then okay. So let's derive U here. Let's derive this equation here. U star. So U, look at this summing junction. U equals U star minus this signal here. This signal is Q times this signal here, which is this guy minus this guy. So this minus is particularly very easy. So it's minus U. And this plus signal is going to be, this is D. Okay. I'm going to do it a little bit quick. So let me know if this is too fast. It's going to be 1 divided by GUVN times psi, okay, then plus here 1 divided by GUVN times GUV D plus U. Let me explain it. I'm doing it too fast probably. So this guy is this minus sign here, so it's minus U. This part is relatively easy. This guy is the signal here. Let me denote this as a B. Let's denote this as F. So this is F of S. Okay, F of S is this signal passing through this inverse of the nominal model. So I have the inverse of the nominal model. And this signal is psi plus, this should be plus, psi plus Vs. So it's psi plus Vs. But Vs is nothing but GUV filtering through D plus U. Okay, so that's the final expression of F of S. Okay? So this is essentially this guy. Okay? I did this, the main goal for deriving this is to analyze how the system response, Vs, is related to U star S. Okay? So after you arrive at this equation here, massage it to make it simplified such that U, so just to do a little bit simplification for this guy, you can arrive at this equation here. Now, this gives us a very interesting result. This gives us Vs equals, you see, GUV times D plus U from the block diagram. Okay? Substitute U into this equation here. You see, the D term is going to cancel with this negative D term, right? And the remaining parts going to be something related to U star and then something related to psi. And this is the final result. So something related to U star, something related to psi. Look at the coefficient. Look at the dynamics over here. Now this is something actually very, very interesting. It says the dynamics between U star and V, okay, this block diagram might be a little bit involved, but this dynamics itself, U star and V, you see, is very simple. It's the nominal model of the plant. Somehow by this complex design, we have achieved this dynamics is just the nominal model. Think about the intuition here. If the plant has uncertainties, it's going to make us difficult to design model-based controllers, right? But by this design, we have somehow make this very big dynamics here to be very simple. This is a nominal model. We know the nominal model. Okay? So this is called nominal model following property. Okay? It follows the nominal model, and it's going to be beneficial for designing model-based controllers. Okay? And second you see here, originally, V is going to depend on the disturbance. Now, after this control design, you see here, V doesn't depend on disturbance anymore. There's no disturbance term here. So the disturbance is canceled in this block diagram construction. Okay? That's just to show you this slide. The main purpose of this slide is to show you that this design has certain advantages. And we have explained this advantage already, that D hat is an estimate of the disturbance here. Okay? We explained this intuition, and here is just the detailed mathematics to explain this intuition here. Okay? Yes? This equation? Let me see. You might be correct. So to see this, it's a good exercise. Let's derive this and see if there are any typos. Let's see, D hat equals QS. QS, so this assumption is if QS is 1, so I won't have this QS term. So it's 1 times this signal here, signal 1 minus signal 2. Signal 1 equals 1 divided by GUVN times psi plus V. V is now GUV times D plus U. And then I think that's it. So that's the signal 1. This is signal 1. Minus signal 2, which is U. Okay? Massage the terms. I'm going to combine the terms about U. I have G, U, V minus divided by G, U, V, N minus 1. I may have even more typos here. U plus GUV divided by GUVN D plus 1 divided by GUVN psi. So take a look. I think I have typos for this term. N here. So there's going to be N here. Then the first term should be minus Is it correct? Let me check the reader. The original equation is what's written on the reader. So I didn't make any typos, right? Did I make any typos? I think this is correct. Anyone see anything unusual? So if this is correct, then the equation in the reader is wrong. Okay, so here, Mm. We already derived U star. Yes. 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 This U should be U star. If I have all these corrections, this should be U star, you mean? Let me see. Maybe that's true. But then what did I do wrong here? Oh, huh? One is based on U, one is based on U star, yeah. But is this correct? I think this is still, this is correct, right? Both ways are correct. So I think one of the equations is using, yeah, one is using U star, one is using U, but both are the two ways to write it. But in either way, the one in the reader I think is wrong, because I copied this from the reader. So remark, check equation DOB-3. Check this equation in the reader and make the corrections. Either way, you can use either way, but this is one way to write it. Yeah, I wrote it in the way of U. Okay, good. So according to the rules, you can have for the homework number 5, you can come to me and I'll give hints of one of the problems over there. Okay? Let's see some details. We will talk about one detail today and then talk about the remaining details next time. So remember, I assumed QS to be 1 for this intuition here. Now, think about what will happen in practice. Suppose my plant is a simple plant, a double integrator. This is very common for mechanical systems, for motion control. Then 1 divided by the nominal plant is going to be S squared. Okay, this term is going to be S squared. Now, you all know that this guy is not causal. What's the relative degree of this guy? The definition of the relative degree is the order of the denominator minus the order of the numerator. The order of the denominator is, the order of the numerator is 2. Because the order of the denominator is 1. The order is 0. So any transfer function that has negative relative degrees is not implementable, it's not causal. So that means when we implement this, for many practical systems, we can't simply assume Q is 1. That's not going to work. So what we need to do is is to do this block diagram transformation. So here, do this. So shift, separate the Q into these two channels to have Q, negative, Q, 1 divided by G, U, V, N. Then here, identity block. So distribute the, then combine these two terms. It's going to be Q divided by G, U, V, N. So the design of Q has to be made such that this guy is, so relative degrees are larger than or equal to 0. Okay. A way to design. One particular example is to do here. One particular example, I have shown 3 examples here. For example, here, the last 2 are simple low-pass filters. You see, the relative degree of this guy is 2. And the relative degree of this guy is also 2. Okay, so this design then implementable causal. In general, this is a structure of low-pass filter that's proposed by some of the early pioneers of disturbance observer design. So use this structure. It's a polynomial of S. And this tau here, I mean, if you be careful here, all these equations have a tau here. Tau is going to define the bandwidth of the low-pass filter. I have written it here, actually. Tau determines the bandwidth of the low-pass filter. In general, smaller tau means larger bandwidth. Okay? Yeah, that's actually is a good question. It's also a question that depends on practice. So in practice, first of all, take a look at the plant, what the dynamics of the plant looks like. And then take a look at the relative degree. See what kind of relative degree for Q has to be chosen to reach the design. And then it includes several trial and errors. Try different Qs and then see how it works. Yeah. Okay, so that's the end of today's lecture. I'll see you next time.